Okay, so this is lecture 8. So we are still working on the device related stuff, but I hope that today we will finish contents related to the MOS transistor. And let's go to the previous lecture, lecture 7. Previous lecture, we have thought about the non-ideal IV characteristics, and first of all, I introduced the mobility degradation due to vertical electric field. What was it? So when we have MOS, usually when we say vertical, then the direction following the MOS step is called as vertical direction. And if we introduce higher and higher gate voltage, then electrons are more gathered underneath of this oxide layer. So if we have high gate bias, then it means that the magnitude of our electric field, vertical electric field, is increased. So compared with relatively low electric field, the average distance of our electrons from the surface is now reduced. Previously, for example, electron gas in its average were placed here, and now we are attracting them with a higher electric field, so they are now located in this part, which is closer to this surface. So this is the interface between what? Interface between silicon and oxide. And this is the interface between silicon dioxide and silicon, and since two materials are different, especially this silicon dioxide is an amorphous material, so usually this interface is not perfect. So if electrons are getting close to this interface, it is more frequently affected by this relative unsmooth or some dirty, some sense, interface. So the mobility is degraded. That was the main reason of our mobility degradation. Where can you see it? So when we draw the universal mobility curves, so mobility as a function of electric field, maybe you remember that it looks like this. So of course in this case you are taking once again logarithmic scale, also logarithmic scale for electric field too, and you can immediately find that there exists two different slopes here. Here relatively moderate transition, and here we have a quite steep transition. The mechanism I have explained up to now due to the vertical field mobility, so or sometimes called as a surface roughness, and that behavior is attributed to the surface roughness. Okay, so bear with me. In the case of our MOSFET, we have such kind of graphs, and we have relative other graphs corresponding to the PMOSFET. Why PMOSFET has 4 holes are having the lower electron or lower carrier mobility, that is due to the band structure and the scattering mechanisms. So this is the originated from its atomic configuration. That was the first topic, and second topic was velocity saturation. So velocity saturation is nothing related with this vertical one. So at the first topic, we considered the electric field along the vertical direction, but on the other hand, other direction which is opposite to the vertical direction, and also connecting our source and drain. This direction is typically called as a lateral direction. So we are now in this second part, velocity saturation. We are now talking about the electric field, however, which is headed along the lateral direction. So simply speaking, when think about this MOS structure once again, but now we have this kind of vector. Let's say if we have this kind of a vector, then what happens in this case? This part can be attributed to vertical component, and this part can be attributed to the lateral electric field. And we are now talking about this lateral electric field, which really drive our electrons from source to drain. So if we have higher and higher lateral electric field, we expect drift velocity of our electrons or holes will increase. Yes, that is quite much reasonable. And what we have assumed up to now was drift velocity is proportional to the lateral electric field, and there appears a proportional coefficient called as mobility mu. Okay, so if we have high mobility, then for given electric field we will have fastly moving carriers. And if we have relatively low mobility, then although we have applied the same amount of electric field, our electrons or holes will move quite slowly. That is the situation of this mobility. And typically mobility of silicon, it does not exceed some values like this one. For silicon, this is not achievable in reality. So if we have really pure silicon, then for electrons we can observe a slightly higher value, but in the case of MOS transistor, this value seems to be the maximum value, or which cannot be achieved by our current technology. And in the case of 3.5 devices, 3.5 materials, then mobility, this one at least 10 times higher or even higher values can be obtained for our electrons. It's perfect. However, in this case, hole mobility, that is quite awful. So in the case of silicon, so even for our PMOSFET in transistor, it's like orders of 100 square centimeter per second, or slightly lower, like orders of 10 something. That can be achieved. So you know that in the case of silicon, although UN is higher than UP, but their values do not show much difference, like 1 orders of magnitude or 2 orders of magnitude. They are similar in the same ranges, same orders of magnitude. However, in the case of this 351, so although that electromobility can easily exceed 10,000, but hole mobility is quite poor. How poor is it? Its value does not exceed that of silicon hole mobility. That is quite poor. And even for silicon, we are now currently talking about the mobility of crystalline silicon. Crystalline silicon means that you are now using quite good high quality silicon wafer. However, in some senses, in some cases, for example, display. You can use, instead of this pure crystalline silicon, you can use, for example, polysilicon, POLI, polysilicon, or you can sometimes use even amorphous silicon. So amorphous silicon has the mobility values even lower than 1 square centimeter per second. So much lower than this value. So you can easily understand this value is not as high as 35 materials, but it is quite good compared with the other ones. Okay, please note this one. Even for other compound semiconductors, some materials do not show much higher mobility than this one. Okay, so what we can see is silicon is quite well balanced device suitable for CMOS implementation. But up to now, we have thought about the relation like drift, drift velocity is just proportional to the electric field, but velocity saturation does say it's not. If we have sufficiently high electric field, then it is just flattened. So if we just draw velocity as a function of electric field and just believe this linear relation, and let's say that once again log scale, please, then what will happen? In this case, we will have a straight line in this log scale, and its slope will be just 1. When electric field is increased by factor of 10, then mobility will increase also a factor of 10. One-to-one relations in this same log scale. However, as we have seen already in our previous lecture content, what was the measured data? So the measured data shows that for low electric field, this kind of one-to-one relationship really happens. However, after that, it knows that it's still one-to-one, but here we have much degraded increase of our velocity, and eventually there is almost no increase, even though when we further increase the electric field. Okay, so are you with me? That is called as velocity saturation. Velocity saturation itself can be observed just in bulk system. Even when you make any kind of silicon devices, not only MOSFET, but BJT, PN junction, whatever, or even pure resistive one, but you can observe this velocity saturation. Velocity saturation is everywhere, and we want to apply it to our silicon MOS transistor. So now when we have a look at the measurement data, this is measured one, of course schematically shown, however that is really measured, and this blue curve shows that okay, there is a certain linear relationship. Please have a look at this one. Here we have made one order increase, and this is corresponding to also one order increase. So if we draw this line suggests that there exists linear dependence between velocity and electric field. Then how about your opinion? So is it good to have a linear relationship? So here you can see, yes, you can see this slope and this slope, that is really corresponding to the linear relationship. However, if we go to high electric field, now it shows that much degraded one. So although velocity is slightly increasing, but actually its increase is so marginal, so we cannot say that this is linearly proportional to this one any longer. So how well now the best relation for our electron velocity as a function of electric field shown here. This is number 2 item and number 3 item. They are typically used to describe the general relation of our velocity and electric field. Okay, so that is the general relation. I mean the frequently used expression for our velocity. So this is, although that is shown here as a saturation, please regard it as a drift velocity. For given electric field, your drift velocity is written here. So the reason why I say this saturation is taken from another literature, so please just try it as your drift velocity. Then as you can see here, it's not that easy to evaluate it, especially this number 2 seems to be quite difficult. When we have electric field, then first we take square and add something and take the square root, and here we have e. So this second item is known to be good for describing our electrons, and this third one is known to be good for our holes. Why do we have a different behavior? So it can be easily understood. So let me just consider. Now let's say that we have two models and we are now increasing its electric field. Now E value is increasing, increasing and increasing. Then what will happen? So here we have electric field normalized by so-called critical electric field. So here we have 1 plus something and here we have 1 plus something. So now you can understand there occurs certain criterion of their behavior. So the comparison between this and that will give us a certain qualitative differences. So think about this one. One extreme is when we have extremely high electric field, then what will happen to this guy? When we have extremely high electric field, then we will have mu effective E that doesn't change. However, compared with this one, this number will be dominant. So here we can just safely neglect it, so then we will have this kind of thing. And in this case, electric field is just eliminated, and we can say that when we have really high electric field, then our velocity will be approaching to mu effective times EC. So this is a given number, so this is just a constant. And please have a look at this third item. So in this third item, also we have a mu effective E and divided by 1 plus something. However, this something is much higher than 1, much larger than 1, then we have the same limit. So our limiting velocity will have the same form. Okay, so when we have extremely high electric field, both model predict what? Predict the saturation velocity called as mu effective times critical electric field. Good. And please consider the opposite extreme. then how can we have the opposite uh, extreme? In this case, we believe that this guy is now approaching to 0. So what will happen? In that case, now we will just have mu effective E divided by 1. And how about this third one? That will give us also mu effective E divided by 1. So you can understand these two models predict the same thing, same extreme case. So if we draw once again velocity versus electric field graphs, so now you can understand their extreme behaviors. So electric field and velocity, then we will have saturated value. And what is it? This is just given by mu effective times EC. And here we have just to slope 1 graph. This is corresponding to mu effective times E. But what is difference between this second item and third item? So it is corresponding to the value near critical electric field. When we have a critical electric field, then what will happen? That is my question. So let's think about a specific number. For example, this ratio of number 2. Then what will happen? In this case, we will have number 5. And in this case, we will have number 3. And if we increase it to number 4, then you can easily understand. In this case, we make a comparison between 1 and EC E over EC's square. And here we make a comparison between 1 and E plus EC. So you can easily understand when we increase electric field over 1, then this squared ratio is much sensitively increasing, rapidly increasing compared to this linear term. So now you can understand for this second model, when electric field is beyond the become beyond the electric field or critical electric field, then it is rapidly approaching to this extreme. So now you understand. If I just draw schematically, if this is a second model, then you can understand the third model shows much moderate behavior, moderate transition from one extreme to the other extreme. So what you can expect is, okay, it will show much slower or smooth transition between this and that. Are you with me? So that is still true for this ratio beyond 1, and even for ratio beyond below 1. Then when we have the ratio lower than 1, this part is rapidly diminishing. So now we have more like a steep or rapid transition, sudden transition between this one extreme to the other extreme. Then let me just ask you one question. Let me come back to our measurement data. Then what is your expectation? Here you have two different graphs. So one for electrons and one for holes. So when you compare two graphs, one for electrons and one for holes, which one shows steeper transition and which one shows relatively smooth transition? So do you have any idea? So people have found that, okay, this electron one shows steeper transition, a drastic transition, and this one shows much smoother one. So, and it is found that the model number 2 is more suitable to describe our electronic motion, and model number 3 is better suited for our whole motion. That is our consensus on modeling this one. However, today we will use a simple model just to give you some idea about what happens if we have velocity saturation. I wanted to say that this is not the state of the art model. So of course we need a better model for our modeling capability, but this is just introductory course. So we will use very simple model for velocity saturation. So this figure 2.15 just to show you a caution about our limiting capability. Although here we have measurement data, however, in this slide, we will just to use a curve fitted to these two graphs. So you can see that in this log scale, it looks okay. So, but you know that although here we have small changes, but this seems to be just logarithmic changes. So please understand this is logarithmic scale. So small change in this scale can be at least in some sense quite big. But anyway, what I wanted to say is although it is not perfect, but anyway, this dashed line shows something good, something reasonable to describe velocity saturation effect. At least when we have a look at this curve, okay, when we have a relatively low electric field, now we have a linear relation. After that, it is saturated, and beyond certain level, then saturation, constant saturation velocity occurs. So I want to say that it's not that awful. So at least we can start from it. So then velocity is previously approximated as this one. So mu times the electric field, just a linear one, and this is only good for this reason. Okay, it is good, but beyond this part, then we must have modification, and simple modification of dividing it by 1 plus normalized electric field, and this normalization constant is called as critical electric field. And please note that if we go to once again, if we go to extremely high electric field, then what happens? Saturation velocity becomes mu effective times what? So if we have a really high electric field and EC, that is shown here. Yeah. So now let's go to this part. Well, previously, maybe you remember our previous lecture material. So let me just, I'm not quite sure. Maybe this is the correct one. So, okay. So this was discussed in our second last presentation, and derivation of our IV characteristics started from the form of our drain current. At a given position, we have the gate to channel potential difference minus threshold voltage. That is corresponding to the number of coulomb per square centimeter, and here we have the width of our transistor. So you already have it. So please have a look at your lecture 6 material. After that, previously you just to consider this form. What was it? This is mobility times electric field. Now you understand when you had this form, simply you are saying that collected electrons and their velocity. Now I want to ask you, what should we do to apply our modification to this drain current expression? Should we change it, this collected electron expression? No, there is no change needed, because this is just a matter of how many electrons are there, and we are now talking about the saturation of velocity. So we can easily understand we must correct this form to have modified expression. So instead of just mere mu times E, now we want to say mu times E divided by 1 plus E. Okay, so are you with me? Then let me just do it. ID equal to something 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 times mu times E times 1 plus E is, oh, it seems quite complicated, but please wait for a while. Then we can just, this is only added term compared with the previous one, so we can just multiply 1 plus normalize the electric field to the left hand side. Okay, so now we can have 1 plus E EC, that is possible. So are you all with me? So then, so this one, the right hand side contains the term related to the electric field, and also a left hand side term, and right hand side term also contains a term related to the electric field. So what we can do is just to say that, just to send it to here. Then ID equal to something, something means that all kinds of this complicated one, and mu plus, sorry, not plus, minus E is the form of our ID. Okay, so are you with me? So I'm just doing simple manipulation, since the only modification we have in this calculation is added 1 plus normalized electric field, and that is moved to the left hand side, and electric field is expressed as ID. Okay, I think that it's enough for sketching our derivation, so let me just come back to our original material, lecture 8. So when you have a look at this form here, that is nothing but just to explain to you. When we express the electric field, previously we had just nothing related with this term, but now due to the introduction of velocity saturation effect, here now we have some additional term. So now you can understand that will do some magic for our velocity saturation effect. Okay, then now the remaining thing is quite straightforward, since electric field is given by just derivative of our channel potential. After that, this ID, drain current, can be considered as just current is just constant over any position x, then simply we can integrate it. I mean that, so let me just delete or erase all of these dirty things. Then we can send dx here, and we can send this guy to there. Then after that we can make the integration from 0 to L, that is corresponding to integration of DVC channel potential from source potential to the drain potential. So integration of this one will give you just length scale, and integration over channel potential will give you this one. So always think about what happens if we don't consider channel length, velocity saturation effect. Velocity saturation effect is found here, and when you have a look at this one, all over these consideration is the same. So this guy is this term, and this guy is this term, and the remaining term, what is it? This is nothing but obtained from our previous one. Oh, well, no, it's okay. So in this case, this is a correct expression, and now we must consider integration starting from Vs and Vd, and here we have Id over Ec dVc. But fortunately, this is just a constant. Id is constant current. So wherever you are, so any x position or any channel potential, this is constant. And critical electric field is also constant. So we can just put it out here. After that, the remaining thing is just Vd minus Vs, and that is written as Vds here. So, okay. So, and any further question? So please feel free to ask me question. So now you can understand when we introduce now additional effect called velocity saturation, now it introduces only one additional terms compared with the previous long channel derivation. So now you can understand. Now we have drain. Previously, without this term, we just divide the left hand side and right side with L. So that was, we had 1 over L, and that was our previous long channel expression. But now we have additional term related to the ID. So what we have is L plus VDS over EC ID equal to blah blah blah. So instead of dividing the left hand side and right hand side with L, now our division factor should be L plus something. Wow, then what will happen? Please think about qualitative description. When we have additional factor, what you can see is, since this 1 over L now becomes 1 over something which is larger than L, so your ID will be decreased. So that is understood. So your current level itself will be decreased always when you consider this velocity saturation effect. So simply speaking, so let me just come back once again. So this is our previous lecture slide, is number 7. Oh, sorry about that. I have to go to number 6. So here we have IV characteristics, and we have three notable observations for our short channel device, and we have understood there is a reduction of current, and the reduction of current, the main reason of this reduction of current was the mobility degradation due to what? Due to vertical electric field. That's true. First of all, this gate-dependent mobility decrease really uh, have the number one priority for reduced current. However, when you go to higher and higher voltage, we have another one. So please once again have a look at it. Here we have a factor, division factor, larger than what? Larger than just L. However, when we have a very small drain voltage, that does not contribute. So simply speaking, here we have degraded slope compared with this long channel description, but this reduction cannot be attributed to our velocity saturation. Velocity saturation doesn't play any role in this part. So this reduction is only due to mobility degradation due to vertical electric field. But here we have some values, and this value is simultaneously affected by two factors. One is gate dependent mobility degradation, and also velocity limited mobility one. Okay, so are you with me? So now we can understand, although the velocity saturation is quite shows quite complicated behavior in reality, but by introducing relatively simpler form for its motion, then at least we can introduce analytically achievable model. Of course, if you want to be quite rigorous, then you have to say that okay, the assumed curve fitting is not perfect, matched to our experiment. So this model cannot be perfect. Yes, you are right. However, we are not talking about just quantitative agreement. If we just consider qualitative analysis, then this one gives us a quite good approximation about what will happen if we have velocity saturation. So simply speaking, good. Now we have reduced value. But please note that there is another one. Is this the only reduction of drain current itself is not the only thing we have to consider in this case. We have to also consider, then, now think about this one. Let's say that we neglect mobility degradation due to vertical electric field, then ID versus BDS. We wanted to draw the output characteristics of our transistor. Then what will happen? Compared with the long channel one, our short channel MOSFET will not show any degradation, because in this case, in low electric field, then drain voltage is quite small, then division factor is still close to 1 over L. However, now we will have a certain knee point transition between so this one, saturation, and here we have some values like this. Sorry about my poor drawing, but you know, this is linear mode and this is saturation mode, and here we have a certain transition point. What was it? Now you should be able to answer this question. This point should be gate overdrive voltage, and that was given by your given VGS minus threshold voltage. And now according to this model, we now understand this is not affected by this velocity saturation. But when you go to higher and higher drain voltage, then we will have lower and lower electric lower and lower drain current, and now we meet eventually the transition point after that, that is shown here. So this is a long description. I'm long. What is the long point of my description? Can you explain why I am long? My description shown in this orange curve here assume that still the transition between the linear and saturation occurs at a point where drain voltage equal to gate overdrive voltage. However, important implication of this model is no, this transition occurs a lot earlier, and after that we will have saturated value. Then you can expect that this saturation current with velocity saturation level can be even lower than this value. Okay, so let me just estimate this expression. Okay, so now can here write down the ID, but this is only good for our linear expression. So now we say that now let's say critical value here. So with this one, this is just a simple reformulation. We just takes it here L, and this is exactly the same as before here. Okay, so then now we understand this factor describe the velocity saturation. Then our question is, what is the transition point between linear and saturation? In the case of a long channel, that was BGT. And how about our short channel device? So now we assume that, okay, where do we have a larger electric field? Source side or drain side? When you increase drain voltage, then usually at the beginning your electric field is evenly distributed. So if we say that X and electric field, then electric field is evenly distributed. However, if you go to the saturation mode, then your electric field is heavily concentrated on the drain end. So are you with me? So please remember this one. Previously, one student asked me about the channel length modulation. At that time, I answered in that way. So when we have sufficiently high drain voltage, then here we have almost no channel electrons. Do you remember? Then now think about the continuity. Here we have tons of electrons, so many electrons, and here we have almost no electrons, but still we have to have what? We have to have the same amount of current and same amount of current. Then how can we maintain the continuity of channel current? In this case, yes, these many electrons are moving slowly, and in this case this small number of electrons are moving quite fast. Then how can we make them move so fast? The only way we can move them is just the electric field, high electric field. So simply you can understand at drain side electric field is higher than the electric field at source side. So if I ask you, where can you find the maximum electric field along the channel in the lateral direction, then your answer should be what? We can find the maximum lateral electric field at drain end of the drain end of our channel. That is our assumption. Then we can say that this condition is corresponding to our saturation voltage, and we say that this is saturation current. So let me just include it. So this is just given to you as your homework problem, but your own exercise. It's not official homework. Please do your exercise. But here, slide number 10 and 11, I have done my own derivation. You can just follow it, and eventually you find these two relations. One is your saturation velocity is simply given by two combination of two quantities. This is a gate overdrive voltage, and this is critical electric, sorry, not critical electric field, but critical voltage. So this is, what is it? This is obtained from here. Critical voltage is critical electric field multiplied by your length L. Then think about this one. Critical electric field, is this material quantity or device quantity? This is only related with your material. When you have silicon's conduction band or silicon's valence band, that is given. But when you have a really long channel device, then what will happen? For long channel device, you will have very high critical field. Okay. Then when you have extremely short device, quite short device, then you will have quite small or quite low voltage, critical voltage. So please keep in mind that critical voltage is a device quantity, not material quantity. When according to the channel length, you can have different numbers. Then now let's go to this one. Once again, first of all, let's assume a long channel device. Then long channel device. Then what happens? Then VC goes to infinity. Then compared with this gate overdrive voltage and critical voltage, which one is larger? Of course, this one is larger. So now you will find that in this case, your saturation velocity now approaching to what? Just to gate overdrive voltage, because you know this term goes to BC, and here we have BC, they are cancelled over, and the remaining thing is just gate overdrive voltage. So from this one we can understand for long channel device, saturation voltage is still gate overdrive voltage predicted by our previous simple long channel IV characteristics. Oh, good. But our next question is, the more important question is short channel device. In this case, we can assume that DC is critical voltage approaching to 0. In this case, now instead of this gate overdrive voltage, now our saturation voltage now becomes to what? Just critical voltage. Okay, because now this one is much higher, so they are cancelled out. Now we have this form. Well, let's adopt this term. So then our saturation current is given by this term, and you know we have, so simply speaking, if we have short channel device, then we have early saturation, then gate overdrive voltage. So my suggestion was, previously we had gate overdrive voltage for transition point between linear and saturation mode. However, if we have quite a short device, then we may have the transition lower than this gate overdrive voltage. Then our saturation value also will be much lower than this value. Okay, so you can then, when you can observe this kind of behavior, of course, in order to achieve this kind of thing, your gate overdrive voltage should be sufficiently high. When you have sufficiently high gate overdrive voltage, then you can observe this kind of behavior. So now let's come back to, then if we have a look at this part, then you can see here and also here, this kind of transition point can be found. So in this time, you can see that clearly this increment of your drain current is not quadratic to your gate overdrive voltage. However, when you have a look at this relatively low gate bias, when your gate overdrive voltage is quite close to number 0 volt, then your this kind of velocity over saturation effect is not that high. So please have a get it. Then, although I have not shown you the full derivation in this part, please do your exercise for this lecture, slide 10 and 11. And now you have long-awaited homework number 2 eventually. Okay, so there has been twice delay of this release of homework number 2. So problem number 1 is like this. Simply, this homework number 1 just ask you to draw velocity field graphs, these graphs in semi-logarithmic scale or semi-logarithmic. Oh, sorry about that. I wanted to just give you this logarithmic scale, the log graphs. Oh, sorry about that. Yeah. Then mobility is just given as 710, and critical electric field is given. This is material quantity. So electric field varies from 100 volt per centimeter to 100 kilovolt per centimeter. So you have to draw 3 orders of magnitude difference in your electric field. Then you will clearly see the difference. So I have one question about homework number problem number 1. To most of you, it is obvious to see the difference between number 2 model and number 3 model. However, here, please have a look at this number 1 and 3. The one studied in this lecture and seemingly similar number 3 are different. I mean that in this lecture, we have not applied this expression, velocity expression, to everywhere. We have limit ourselves only to linear mode or electric field is sufficiently low. Then please don't be confused. So beyond a certain level, we have just a straight line, and this is not. We have a much smoother transition for our model 3. So please just draw it. However, see that now this is the second problem, and draw your output characteristics of an N MOSFET by using two IV models. So already you have the IV model, then long channel 1 and short channel 1. It's okay. Then since that is output characteristics, you must draw your ID as a function of what? ID of function of your VDS. I have tried to give you every detailed parameters to you. I think that it is enough to perform this problem number 2. So if you have anything uncertain, then please show your choice about parameters. No further parameters are given to you, but I hope that this is quite much enough to draw your graphs. Okay. Now, okay, so if I have to summarize our lecture up to now, is now we have considered the velocity saturation. Of course, previously in the last lecture we have considered also velocity saturation, but at the time it was just qualitative one. But today we have introduced a simple, crude, but okay, reasonable model to model our velocity saturation effect. And the main lesson from this modeling was quite clear. Of course, we have a factor like 1 point VDS minus VC. We have an additional factor for reduction of drain current. So reduction of drain current is important when we have higher electric field, not approaching zero. Also, we have another one, VDS, saturation voltage is also affected for short channel device. Then it is no longer saturation voltage is no longer gate overdrive voltage. Instead, we have a much lower value for saturation. So that was so now think about this case. So we have studied quite a lot about characteristics, but as a user of this device, which one looks better, short and long? So now assume that you are placing your device always in the saturation region. Then what you wanted to have is just changing your gate voltage. I wanted to increase or decrease the gate voltage, and just wanted to measure change of ID. So my desire is to make a quite sensitive device which is sensitively affected by VGS. Then my question is, think about the expression for your ID. Now here you have the form like this. When you have this kind of ID, then how about your ID? For long channel device, you remember that your saturation current was just proportional. Saturation current was just proportional to VGT and its square. So when you change your gate voltage, then of course your gate overdrive voltage changes and you will have a quadratic dependence. But if you have short channel expression and something when you have quite small critical voltage corresponding to short channel device, then what will happen? In this extreme, this part just reduced to what? Just linear dependence of your drain current, drain saturation current with respect to gate overdrive voltage. So now when you just increase or decrease your gate source voltage, your desire is to have super high value for your ID or completely vanishing value or much smaller value for your saturation current. But compared with this long channel device, unfortunately this short channel device is much more moderate, smooth value or dependence on the gate bias. Okay, so from the viewpoint of just a user of this device or designer, this short channel effect is not that desirable. So we want to have more sensitive dependence. So we will see this difference later in this lecture. Please remember that. Oh, okay, so from the viewpoint of a saturation current, short channel effects just to reduce the sensitivity of our transistor with respect to the gate voltage. Yes, now we have 10 more minutes and we will spend our time to discuss about the body effect and finally leakage. Then that will be the end of our lecture, and next Tuesday we will move to the inverter. One is body effect. Body effect, nowadays unfortunately we have 3-terminal device and we have no the first terminal called as body or sometimes substrate. And what is body or substrate? And in the case of our MOSFET, that is corresponding to our P substrate. So do you remember? So when we consider NP and we have introduced another P plus reason connected to the metal line, so this P tap can provide the ground voltage to our P-type substrate. That was explained already. However, what happens if we have positive value instead of ground, or negative value instead of ground? Then what will happen? Please think about this one. If we have a positive value for our P substrate, this is quite a bad situation. Why? Here we have N corresponding to our source and drain, and this is P-type substrate. And think about the case where source is grounded as usual. Yes, now source is grounded and now P-type substrate is positively biased. What is it? Then this PN junction, source and substrate PN junction is biased in its forward mode. So now we can expect that there will be a certain non-negligible current flowing. So usually this is not a desirable case. Okay, so forget about this positive one. Then, of course, if we apply quite a small positive value, then maybe the leakage current is only slightly increased, but anyway, this is not a good choice. But instead of that, think about this negative value. Then what will happen? Now, if we apply negative value to our substrate, PN junction is placed in its reverse mode, so we don't have to worry about the leakage current of this PN junction. So, well, then What's the matter? The point is, if we have different substrate voltage, then we can control the threshold voltage itself. I mean that, simply speaking, when you have negative voltage, in the case of an MOSFET, if you apply, for example, minus 1 volt to your body, then your threshold voltage is now become higher compared with your threshold voltage when your body is grounded. Okay, so simply speaking, by applying negative voltage to your substrate or body, then you can increase the threshold voltage. So what is it? Why it is important? Why it is important? So increasing substrate or increasing threshold voltage is sometimes quite important. Think about this one. Let's say that here you have a transistor. So your VDD is given. For example, 0.7. So in order to maximize your here you have applied also VDD, and in order to maximize your drain current, on current, what you can do is your threshold voltage is reduced. So are you with me? If you remember correctly, then our IV characteristics always have the terms like here, terms like gate over drive voltage. Whether that is linear or whether that is square, doesn't matter. Anyway, we have something like a VGS minus VT term. If we have a lower threshold voltage, then we will have a higher drain current. So are you with me? So in order to maximize the drain current, usually that is the target of our high performance device, we wanted to have lower threshold voltage. But what happens if we reduce our threshold voltage too much? Then immediately we have too high of current. This is not acceptable. However, you know that by controlling our body voltage, then we can selectively increase the threshold voltage. So theme is like this. When we turn on our device, we just bias our body 0 volt. Then we will have just normal threshold voltage. But when we wanted to turn off that device, then please apply a negative bias voltage. Then what will happen? This one will increase your threshold voltage, and this is immediately affect the op current quite much reduced. So this technique has been used in reality when designers are running or designing something. Then by controlling the well potential or substrate potential, then when certain area of the circuit should be turned off, then they can apply this technique to globally increase the threshold voltage to save the leakage current. Finally, I wanted to say that this is our final one. You know that now everybody in this classroom understand this is input characteristics. And this input, when you have a look at this input characteristic, you can draw it as a semi-logarithmic scale or linear scale. And this one is a semi-logarithmic one. And most important quantities in this graphs, so this is here, this is corresponding to on current, and here you have the off current. So depending on the device options, you can control these two values, and this ratio, their ratio is quite important. For high performance, that ratio is not that important. For low power device, that difference is quite important. Then here in this last slide, the textbook explain something. However, although that is the last slide, that is a kind of one of the most important topic here. Please understand these are different. Although shown here, this concept and these two concepts are different. This subthreshold slope means the slope shown here. In semi-logarithmic input graphs, then you can find a certain slope here, and this slope is typically have this form, the unit of millivolt per decade. Simply speaking, in order to increase your drain voltage, or drain current by factor of 10, how much voltage increase is required? When you have 100 millivolt per decade, means that when you increase your voltage from 0.0 to 0.1, 100 millivolt, then your current is exactly 1 orders of magnitude higher. Are you with me? So now I want to give you one typical value. For example, if we have this kind of slope, SS equal to 60 millivolt per decade, then what does it mean? Then when you draw VGS and ID, and when we have this subthreshold graphs corresponding to this part, then when you increase this gate voltage only by 60 millivolt. 60 millivolt is corresponding to 0.06 volt, and when you increase 0.06 volt, then you will get 10 times larger drain current. This is the meaning of subthreshold slope. So since this concept is too important, so I have to stop here and continue our discussion for this subthreshold slope once again. Sorry about this delay in lecture progress, but this concept is one of the most important one in this device characteristics. So please understand the situation. And do you have any question? No? Then let's wrap up today's lecture.